Okay, differential equations. Okay, let's start with an example to motivate what we're trying to do here. So imagine you have a field, a fenced-in field, and you have some rabbits in this field. And we'll say let y equal number of rabbits at time t. And then you have dy dt is the growth rate. Okay, so rabbits being rabbits, they will reproduce. So there is a growth rate. So we'll make a simple assumption here, which I hope you'll agree with, is that the more rabbits I have, the higher the growth rate. Okay, we'll say in math, we'll say that dy dt is proportional to how many rabbits I have. Well, that's why. So that's English, but in math, we say dy by dt is proportional. You put this fish-looking symbol, is proportional to y. So what does proportional mean? Well, it means the dy dt is some multiple of y. So we'll say k times y, where k is a constant. Okay, so what are we going to do with this? We are going to say, well, this is what's called a differential equation. So it's an equation that involves a derivative, at least one derivative. Let's guess a solution. So guess a solution here. So we're looking for a y. Okay, so the solution is the function y. Okay, so we're given some information about the derivative of y, and we would like to find y itself. So what are we told here in this blue rectangle? We are told that the derivative of y is just y itself times some constant. So let's do some thinking here over on the side. If I had dy by dt, oops, if I had the derivative is just, let's say 1 times y, then you would say, okay, which function has as its derivative itself? Okay, so which function, when I take a derivative, I get exactly what I started with? Well, that's going to be um, e to the t. So that's not quite what we have in the blue rectangle. We're going to have to modify that a little bit. We don't have e to the t. We're going to have to throw the k in there. So y is equal to kt. E to the kt will work. Okay, so let's verify that this guess is correct. We'll call that an example. So we'll say verify that y is equal to e to the kt is a solution of the differential equation dy over dt is equal to ky. So how do I verify that? Well, let's do another thinking in red over here. So x is equal to 2 is a solution of x squared plus 2x minus 8 is equal to 0. Is that right? How can I verify? How can I verify that? Well, I can just take this x is equal to 2 and plug it in here and see that I do get a true equation. I do indeed get 0 is equal to 0. So that tells me that my solution here is verified. Okay, so that's exactly what I'm going to do in my example here. I'm going to take this y and plug it in here and here and just see that it works. Oops. So I took this, plugged it in here, and plugged it in here. And I'm just going to check that it does work. Okay, on the left-hand side, I need a chain rule. So I get e to the kt times the derivative of the inside function, and that does indeed equal the right-hand side. Okay, so that verifies. Okay, I have checked that this function works here in the same way that x equals 2 works here. Okay, let's try an exercise. Verify that y is equal to c e to the negative x plus x minus 1, where c is just some real number, is a solution of y prime plus y is equal to x. Okay, so pause, copy, give that a try. Pause, copy, try. Now all I'm doing is taking this expression and plugging it in for y here and here. So I get y prime plus y. Does that actually equal x? Well, here's my y candidate. He's applying for the job, and we will see if he is successful. So we're going to work out the left-hand side, and we get cancel. Oops. We do indeed get a true equation at the end.